So now we're going to come back to the relative refractory period and take a look at its importance in how stimulus intensity is translated in a single neuron. And we're going to use a sensory neuron as an example. So here's the setup. I want you to imagine that you've got your eyes closed and your hand out, right? Or maybe just your arm, something like this. And somebody is taking a very fine point, finer than this even, like a needle. And they're just barely touching it. Here, I'll do it on the side here. They're just barely touching you. You have sensory neurons right there. Sensory neurons that are sensitive to touch or pressure. And if they're barely touching you, those sensory neurons are still signaling that information to your brain and you register that touch, right? But what if they press harder? Now the same sensory neuron is able to convey that to the brain as this is a harder touch. So it's the same neuron conveying that the stimulus is stronger, the pressure is stronger. How do they do that? How does one neuron convey to the brain that not only are you being touched, but you're being touched with more force than you were before? And so that's the premise of this particular lecture. So before we look at how this works, I want to revisit the relative refractory period. So in this image here, I have an exaggerated action potential. And down here, I have time, and this is milliseconds. And our resting membrane potential is minus 70. So to start an action potential, I need to climb to minus 55 millivolts. But once I do that, then an action potential is going to be generated, and the absolute refractory period ends somewhere around there. Now at this point, a subsequent action potential could happen, but look at what we would have to do. We would have to now make the climb to there, which is a lot harder to do than the first climb we had to make. The first climb was plus 15 and now it's like plus 25. So this represents the relative refractory period. Yes, you can generate a subsequent action potential, but in order to do so, you need to have so much depolarization that you immediately go from here right back up to the minus 55 threshold and therefore immediately start a subsequent action potential. If that part of the membrane is experiencing some depolarization, but maybe it's only this much of a difference, then we have to wait until that relative refractory period is over until we can make that jump again and start another action potential there. So look at the difference in terms of number of action potentials that would be propagated down the axon and to the axon terminals. Since the absolute refractory period is approximately 2 milliseconds, I could, with enough stimulus, potentially be sending action potentials every 2 milliseconds, which would mean that I could send 500 per second. But if my stimulus is not that strong and only gives me a jump of plus 15, then I'm going to be generating action potentials once every 4 milliseconds for the duration of the stimulus. And in that case, I would only send 250 action potentials per second. So the frequency of action potentials that are sent down the axon corresponds to the level of depolarization in a sensory neuron. And the more depolarization you have, the more frequent your action potentials can be. And so your brain interprets this as intensity. I'm going to come back to that drawing to give you a more detailed example of how stimulus intensity could correspond to increased depolarization. But for now, all I want you to see But for now, I draw you to the book's picture that shows this. In this example, we have a sensory neuron. And sensory neurons, you might notice way down here, have a totally different morphology. They often keep their cell body out of the way, and they may even have two different axons. What I wanted to show you is that if this is still the trigger zone and this is where the stimulus is, you could presume that where I've just circled is like a dendrite or a cell body. If my stimulus is weak, then by the time I get to my trigger zone, you can see I don't generate very many action potentials. That will release a small amount of neurotransmitter. But if my depolarization is much greater, then by the time I get down here to my trigger zone, I still have a lot of depolarization, which means that I'm able to generate action potentials every 2 milliseconds, and that's going to correspond to an even greater amount of neurotransmitter release. Okay, now let's come back to my detailed example. I'm going to assume that this neuron that I've drawn is a sensory neuron that responds to pressure from touch. And so each of these gated channels that you see embedded in the dendrites are going to be mechanically gated sodium channels. So now let's come back to my skin idea. And I have a pencil and I'm barely touching. If these are mechanically gated sodium channels that are embedded in there, they are literally squeezed open from pressure. So you can almost think of it like popping a pimple. You squeeze it and then the pop goes, whip, pop, pops open. So if I'm barely touching my skin, then maybe that's only enough pressure to pop open the dendrites that are closest to where this tip is. So in my example, I'm going to assume that it's right here. So we're just going to open those, and that's going to allow sodium in, which is going to create actually a pretty strong depolarization at this very point. But we know that that depolarization will dissipate as it moves towards the axon helix. So maybe by the time we get to the axon helix, my membrane potential is barely over threshold, and I start action potentials, but only 1 per every 4 milliseconds. So my brain is getting 250 action potentials per second, and it assumes that is a weak signal. But let's say that I take this and I start pushing a little bit harder. Well, that's going to open up nearby gates. So now we're going to open these as well. That's going to allow more sodium to come in. And that means that it's going to add to my sodium influx such that I bring this membrane potential up a little higher. So now maybe I'm running an action potential once every 3 milliseconds. Well, now I'm going to push even harder. And that's basically going to open all of these up. And so that's going to allow a whole bunch of sodium in. And now I'm going to have lots and lots and lots and lots and lots of depolarization from all of that spatial summation. So much so that as soon as one action potential ends, another one will start. In other words, I will get my 500 action potentials per second. They're running every 2 milliseconds, and my brain interprets that as maximum stimulus for that neuron. Of course, it won't just be one neuron that's sending information. Nearby neurons may also send information that then all gets integrated by the central nervous system to interpret the strength of the stimulus. So the importance of the relative refractory period is to vary the number of action potentials that are propagated down the length of an axon in response to different types of stimulus. When the stimulus is very strong, then you might have a really strong depolarization, which will be converted to more action potentials per second. And when the stimulus is weak, you'll have just barely above threshold depolarization, which will translate to an action potential once every 3 to 4 milliseconds. And therefore, it will be interpreted by your brain as weaker stimulus. All right, that concludes this lecture. I'll see you for our final neurophys lecture on case study for neurotransmitters in the next one.